Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am very happy to have Andriana Strezoski with us and Allan Treiman with us today. Hey, Andriana. Hi, Allan.
Hello.
Hi, Allan.
Well, thank you so much for agreeing to talk about your very lovely PSJ article.
Thank you.
Mm-hmm.
Thank you for having us.
Oh, yeah. Great. And Andriana, what's your geolocation? Where are you located at?
I'm in Anchorage, Alaska, pretty far up north over here, and it's just now getting like daylight.
I think this is the first time had an author from Alaska, so that's great. Are you north above the Arctic Circle? Are you a little farther down in Alaska, or?
Oh no, this is pretty south, south central. So
Okay.
this is Alaska. Oh gosh, right around here.
Very cool. Very cool. And Allan, where are you located at?
I'm in Houston, Texas, where it's actually a little chilly today. It was in the low this morning was in the 40s with this beautiful clear blue sky, and I'm looking out the window watching the birds bop around in our trees.
Very cool. Let's see. And I'm in Phoenix, Arizona, and so we will a little cooler today. We'll probably get up into the mid 50s or something like that, but otherwise very nice. So cool.
Yeah.
Very good. Allan, what do you like to do for research?
Yeah, I've been doing planetary and geology research for a long time. Mostly I do chemistry stuff, which is where I got my degree, and that sort of leads into the project here. A lot of my time I spend on Mars because I work with both Mars missions, the MSL rover and the Mars 2020 rover. So yeah, mostly that kind of stuff. I'm sliding toward retirement, so trying to find other stuff to do besides this part that I love so much.
Awesome.
Yeah.
And Andriana, what do you like to do for research?
I'm very new to that field, actually. I just graduated with my bachelor's in geology.
Congratulations.
I've done this research project on Venus with Allan back in 2021 during the LPI internship.
Oh, yeah.
But I've also done a little bit of research on Europa as a student research project. Wasn't developed enough for like anything. It was more just student experience.
Good experience. Good experience.
And now I'm doing environmental related work.
Very nice.
Back to Earth, just figuring stuff out what I want to do before I go back to master's.
Very cool. Very cool. Well, congratulations on your recent graduation.
Thank you.
And that is going to bring us to this very awesome Planetary Science Journal article, and it's open access, people. You can go get a copy for free. Go grab a copy. The snow line on Venus's Maxwell Montes varying elevation implies a dynamic atmosphere. And Andriana and Allan, take us away.
Okay, I'll start with this. We don't know Venus very well because it's got this incredibly thick atmosphere. So if we look at it with visible light or near infrared, all you see is its clouds, which are sort of cool on their own, but they don't tell you anything about the surface. So all we know about the surface is from radar. And the Magellan spacecraft, gosh, in the 90s is our best source of that radar. And it's been studied off and on, well, since then. And one of the really interesting things about Venus, and if you can go to that first slide, is the highest mountain range, Maxwell Montes there, which is it's really hugely tall. Its highest point is 11 kilometers above the average elevation. So this is an incredible mountain range. It's like Tibet only on steroids.
Right.
So one of the coolest things about it, as you can see in this radar image, is that at the highest elevations, it's much brighter in radar. Whatever's at the surface there reflects more of the radar back than anything else around it. And so that's been one of the big puzzles about Venus, is what this means, and particularly, what the chemistry of it, which is where I fit into it, the chemical composition, what's different about the surface that's so bright in radar. So that was something that Andriana and I started looking at. We were looking sort of in general around there, and whether we could figure out anything in particular about this radar stuff. Really all we have to work with is this one data set. So, we have this data, and anything beyond that is just speculation. So what we went back to the data set and started looking at it. And at that point, I guess, Andriana, you want to talk about how you got the the colored lines here?
Mhm.
Yeah, absolutely. So we pretty much use the elevation, emissivity, reflectivity, and the synthetic aperture radar rasters off of the USGS um, astronomy page, correct?
Yeah, this is a map of
Um,
places, but yeah,
Mhm.
yeah, we
it's the
downloaded the
Magellan
files.
data.
Yeah, we downloaded the files from there, and then we used ArcGIS and
Mhm.
JMARS occasionally. And basically, we wanted to see how the elevation and the reflectivity, what their relationship is. And since the initial thoughts were that Venus is generally like the same all the way around, although varying with elevation, we wanted to see like, would this line be at equal elevation? Because if there's a chemical change at this line, like,
Okay.
you know.
Yeah.
So we traced it starting on the northwest corner over here. Um,
Sure.
and the reason why I chose these lines was just like as a visual representation to section it out so that it's more visible on the graph itself when we plot it. And that made it very easy to notice that the southeast section is a lot lower elevation than on
Mhm.
the northwest.
Mhm.
So
Yeah.
Yeah. And so this is a contour.
yes.
Well, it's a contour of radar brightness, not elevation. Yeah.
Yeah.
I should also mention that it's not like a solid line. When you zoom in, it is very much like a gradient, kind of like powdered sugar on a cookie. Like
There
you
you
can
go.
see the circle, but it's a very faded line. So there is some guesstimation going on.
Understood.
Yeah.
Understood.
Yeah. And, you know, if I can interrupt just a little bit more background for folks that don't know radar and Venus, you know, we're looking at radar that's comes from a satellite, the Magellan satellite going around Venus, shoots down to the surface and is reflected back up. What you see there, there are bright lines that go sort of northwest, southeast, upper right to lower, upper left to lower right. Those are ridges in the mountain range. Those are like individual ranges in the Maxwell Montes Tibet-like area. Cleopatra, that's noted on the right there, that's a big impact crater, and it's a little bit lower elevation, which is why it's darker. So it's the same kind of dark color as the lower elevation surrounding it. So it's sort of like a hole in this mountain range.
Mm-hmm.
To the left of it, there's dark flat stuff, and that's a flat lava plain. No, further left than that, Frank.
Over here.
Yeah, down from that. Yeah, you're right in there. That's a big flat lava plain.
Got it.
And the mountains, Maxwell Montes, it's a really, really sharp scarp at that edge. That's where the blue colors are.
Mm-hmm.
And that's one of the issues in doing this work, is that radar doesn't do really well on really, really sharp scarps. It's hard to correlate elevation and radar reflection. So we think that's part of the reason the blue area bounces up and down so much. It's sort of an artifact of the radar. I mean, you can see, like, comparing the red and the yellow parts with the blue. The blue is absolutely nuts.
Yeah.
Except at the very far right end where it's pretty consistent. We think that's artifacts from the radar. It doesn't reflect real changes in the elevation on the surface, the elevation of that snow line.
Yeah. Very nice.
Yeah.
I'm with
Yeah,
you.
I remember seeing this for the first time. It's like, that can't be canyons right there. That's fantastic.
They are very steep and very big.
Yeah.
Yeah. Very
Yeah.
nice. Very nice.
So
So what is the let me just ask, what is the resolution of the imaging?
So I think the best resolution that was available was
it's about 75 meters per pixel on the radar. Yeah.
something like that. And
Okay.
that was at the best areas, and then lower from there.
Yeah. So you know, each spot that we can see is about the size of a football field, a football pitch.
Very good.
It's not really very good compared to what you can see for the Earth or for Mars, but that's one of the issues with Venus and its thick, nasty atmosphere.
Mm-hmm. Mm-hmm.
But there are new missions.
I will come back to that.
Right?
Okay.
Yeah, we'll come back to the missions toward the end, I hope. Yeah.
Yes.
Yeah.
We'll come back to that. Very
Fair enough.
good. Okay.
Yes.
I'm with you. And here we got some of the results, the snow line elevation. And you want to talk about figure 2?
Yeah,
You can go there.
go ahead, Andriana.
Alrighty, so I'm gonna focus a little bit on the lower image first, and completely ignore the orange and the purple line for now. Only look
Okay.
at the gray dots.
Okay.
So we created, so all those gray dots, those are points of elevation versus emissivity.
Oops.
And it's a recreation of
Yes.
a data set from Close et al. We wanted to see if this signature is going to be the same, and maybe see what that means. And initially we thought that these points where they're clustering, gosh, how do I explain this?
Yeah. Hey, can I interrupt a sec on that and talk a little bit about emissivity and reflection?
Yes, please do.
Yeah. Yeah. The radar system on Magellan, it emitted radar to the surface and saw what bounced back, but it also listened to the surface, looked at it to see what kind of radar waves were emitted from the surface.
Okay.
The surface is hot enough that it emits radar waves all on its own. So that's sort of, there's sort of two parts of this. There's the emitted emissivity and the reflected, reflected stuff.
Cool.
In theory, those ought to be complementary, that, if you add them together, they should be one unit.
Mm-hmm.
And so, a variation in one ought to be the opposite of a variation in the other, right? So that's sort of what we're looking at here with the gray dots, are the emission from the surface.
Got it.
The lines that Andriana will get to in a second are the reflection from the surface.
Right. So
Right.
if we only focus on like the clustered gray area of this image, initially what was thought is that emissivity decreases with elevation. So if we start on the far right corner of this cloud of points, and then if we move to the left side, it increases. And everything above that, we thought that was just noise because it's all these scattered points.
Yeah.
And so we thought it's just this trend line, it's just this flat line that goes like, I guess, camera, whichever way it's oriented, but it's just a flat line.
Yes.
But on the image above, we drew these two profile lines to see if that's true. Will they follow the same trend? But instead is what we get is this curve. We get a decrease in emissivity up until 6 to 8 kilometers, and then emissivity just turns back around and increases again. So that was just one of the little anomalies that we noticed during this research.
Yeah.
And just to orientate me a little bit, B here has a beginning and end. So is this end correspond to this point, or is it the other way around?
Yeah, that's correct.
Yes. Okay.
Yeah.
Yep.
Yeah. And another thing you can see from this graph, it's the same as in figure 1, that the A profile, which is further north, has higher elevation than the B profile.
Let's go back to figure 1.
So that's sort of the same thing, that line A is up where the green stripe, the green boundary is on figure A.
Okay.
And B is down sort of at the red-yellow area.
Yeah. Okay.
So it's just a reflection of the same thing, that there's a real difference in elevation.
Okay.
North to south, northwest to southeast, and that what these other people, Close et al., did way back in the 90s, and they got this huge cloud of data. Well, a lot of that is related to latitude. It's not just that the data are so scattered, but like you can see here, the southeast has lower elevations than the northwest.
Right. It was just really fascinating to see the curve on the line rather than just seeing the same trend line, like a flat line.
Right.
So that was I thought that was really cool.
Yeah.
Very nice.
That was really nice. Yeah.
And then we got figure 3, additional cuts. More.
Yeah. So more profile profile images. And on these ones, we plot emissivity, reflectivity, and elevation across a distance to compare the 3.
Okay.
And from my understanding, it's reflectivity that has a direct relationship with elevation, meaning as elevation goes up, so does reflectivity, or so that's supposed to be the standard. And emissivity is supposedly the inverse of reflectivity, but we clearly don't see that in these images. moving from left to right,
Uh-huh. Uh-huh.
we see that there's a pretty big dip in both emissivity and reflectivity around
Okay.
6 or 7 kilometers of elevation.
Okay.
Or am I wrong here? Hold on.
Yeah, that's right. Yeah. Yeah, as you can sort of see from the first half of the image, in the center of Maxwell, it's a little darker than it is at the edges. Like, wish I, if you go along profile one about about a third of the way from the left side, yeah, right in there, it's a little bit darker, and that's a real thing. The radar reflection is lower there, and the radar emissivity, which is sort of the inverse of reflection, gets high, and you'll see that on graph B1, which is that first traverse.
Profile. So B1 is profile 1. Oh.
Yeah, yeah. Uh-huh.
100,
And,
8, yeah. Okay.
something that shows up in the appendix here is as I said, the reflectivity and emissivity should add up to 1, more or less. And what we showed in the appendix was that they add up mostly to 0.9 to 0.95, which is close enough considering everything, except in the area of Cleopatra Crater, which is bizarre on its own. That's a separate really interesting issue. But yeah,
Yeah, Cleopatra is that big dent on the far right of the first profile graph.
yeah.
Yeah,
that
we can see
impact
it clearly in the lines too.
Right there.
Yeah.
What drove the what drove the choice of these 2 lines for the profiles? I mean, you could draw any 2 lines. Why these 2?
I actually did about, goodness, I made so many different lines, but for different trials and errors as well. But I'm gonna say about 10 at least. And then we chose the 2 that are most representative or
Okay.
had the most like discrepancies to show like, hey, this doesn't go based on the standards we thought it would go.
One's more interesting than others. Okay. Very cool.
The cool thing to see from that bottom profile B2 is to look at the black line, which is elevation. And it's pretty flat on that plains, but then there's that incredible rise within a few tens of kilometers. It rises from 4 to 10 kilometers elevation. That's a really, really steep. So, that's like the front of the Himalayas.
Yeah.
I could also mention that's like the blue line where we noticed it's very jagged and the elevation was sharp increases and decreases.
Yeah.
The blue line I'm referring to is from the first image, by the way.
Oh.
So unless it's one of those little.
Oh, the blue on figure 1. Yeah,
yes.
that's where it was so jagged.
Yes.
Yeah. Lower part there. Cool.
Yeah. So, yeah, that was why we picked those. I mean, Andriana made tons of cross sections across both east, west, and north, south, trying to make sense of it all.
Nice.
I don't know that we did or not. At least AAS was
an average
military
one.
science was willing to publish it, so it couldn't have been too stupid.
Very cool. No. Very good.
So something that Andriana had mentioned just briefly in there was that this was a really unexpected result because Venus has sort of been considered, sort of like one-dimensional atmosphere, that it's the same composition and everything from the surface up to, say, the clouds, no matter where you are on the surface. So people do these, they say, well, we have one dimension, we have this one traverse of temperature and whatever. Well, that's everywhere on the planet. And
there is data that supports that. That's why. Weren't there probes that measured temperature at various areas, including they didn't land super far north, close enough to Maxwell, but there was one relatively in that area, and that also measured pretty much the same temperatures.
Yeah. So that was, there was evidence to believe that, but yet what we found, depending on what model you take for the what the snow is and how it got there, it seems wrong. If the snow is like, snow on Earth, it's going to come out with freezing temperature, and it's basically going to be the same elevation. And that was sort of the model that everyone had said. With this atmosphere that's the same everywhere, maybe, the elevation of that snow line ought to be the same everywhere,
right.
Instead of being like this, which is how we found it. It ought to be just flat. Boy,
Mhm.
having the camera so close makes my hands look huge.
Very good.
So,
Snow fingers, snow lines. Awesome.
yeah, so that was a really strange thing, and we started thinking about how that might be possible to reconcile those two things, and that was sort of where we ended up with this thing in the title of dynamic atmosphere of moving
Right.
wind surface.
Right.
And
But
so,
before we got to winds, since that's not our specialty here, we're geologists, right? We looked at what are some geologic signs that we can look at. And there were definitely those ridges, like in figure 1, those lines. That's like, oh, there's some kind of mountain building going on here, and that could create some tilting. So if the snow line existed prior to tilting, like, okay, that makes sense why it would be elevated on one area and then not as much on the other area.
Okay.
And we also see Cleopatra. I looked at Cleopatra a little closer in a couple of my cross sections during the research.
Okay.
And the crater, the most inner ring is actually filled with lava, if that's still correct. And fluids like to flow on a horizontal surface, right? Cleopatra is actually tilted. So that also gave us a clue, like, okay, maybe there is some kind of regional tilting going on with this mountain, uplift, erosion, whatever.
Okay.
And then later on, we came across some papers that talked about wind models on around the entirety of Venus. And they looked at during the daytime, during the nighttime, and we focused in on Maxwell. And the direction of their winds was actually very consistent with what we're seeing here.
Okay.
With winds starting from the southeast, moving up the northwest. And if this cloud is pushing precipitants or the chemicals that react with the rocks or whatever, it would be going in that direction, going up the mountain from
Great.
southeast to northwest.
yeah,
Nice.
this is sort of the concept of a snow shadow or rain shadow. Like, if any of your listeners are in California, for instance, the weather mostly comes off the west, which is doing very hard now. And if you go in the Sierras, the Sierras are wet. They have lots and lots of rain and snow. And as soon as you cross over the Sierras into Nevada and very easternmost California, it becomes a desert. And it's because the mountains have sort of squeezed the water out of the atmosphere, and then it goes over the mountains and there's not so much anymore. So that was one of the ideas here, possibly, is that whatever's coming out of the atmosphere is getting squeezed out as it goes over Maxwell. And so by the time you get to the northwest end of Maxwell, there's not so much of whatever it is to precipitate out or react.
Okay.
So that was the other concept we worked with.
Right.
There's also just the morphology of it, right? It's not circular.
Oh, no.
So yeah.
Yeah. So but the atmosphere stuff, I think the modeling of that is still in its infancy. There's still some very strange things that have to do with the atmosphere, but it's real hard to see because, like I said, Venus has this huge cloud deck, and we're talking about stuff underneath the clouds. So trying to see through the clouds to see what the atmosphere is doing under the clouds is really tough.
Right.
Cool. Okay. I'm with you. Very nice. Very nice. Very, very nice. So, Andriana and Allan, I want to thank you so much again for sharing your very lovely article with us. And you hinted at it a little bit at various points there. And so let me ask, where do you think we go over the next, 2 to 5 years on this topic? Are there any upcoming missions that might be able to probe or, a 2023 set of electromagnetic signals, something along those lines? Is there laboratory astrophysics to be done? So just sort of next steps on where you think we go over the next 2 to 5 years.
I'll let Allan go on that.
Oh, okay. Yeah. There's an awful lot that can be done and is being done. You mentioned spacecraft missions. The two that are at the present going to fly are going to help to some extent. The Da Vinci mission is going to go through the atmosphere and land or hit the surface. They hope it survives the landing. But what it'll do is it'll give us a really good chemical composition of the atmosphere, and that'll help us understand, how the atmosphere varies with elevation, how the wind speeds vary with elevation. Unfortunately for us, it's going to be right near the equator, and we're way far north, where it's 70 degrees north. So, it'll be helpful, but not necessarily all that much. The other mission, the Envision mission, which is a European Space Agency one, that will have a radar system on it that'll have better spatial resolution than Magellan did. So we'll be able to go a little bit better and look at the elevation relations of it. It'll also be able to do an experiment that just really wasn't possible with Magellan, which is to take radar from the spacecraft and bounce it off the surface and receive it at Earth. So the geometry that Magellan had, it just goes down and back the same way. This other one, the radar will come down and then will reflect off and go off back to Earth. And that difference in angle is going to provide some really good constraints on what the substance might be.
Is InSight designed as full planet?
It's not. It's an Envision.
And is Envision full planet?
Yeah, it's an orbiter.
Yeah, cool. Okay.
Yeah. The other thing it has is an infrared system. There are just a couple little thin windows in infrared light that can image the surface, and those may help a lot. It's not real clear how well, but that's something they'll be working at. Another thing we can look at is Earth-based radar. That's been done out of Arecibo, which unfortunately is no longer working. But they've made really big strides in making long baseline radar. So like if they can do, Goldstone and Jodrell Bank, for instance, in the US and in Europe, they could use those together. It's like having a single radar system that has a dish as big as the Earth. You get really, really good spatial resolution, and that might be coming too.
Nice.
Yeah. We're sort of starved for data on Venus. That's really a big problem. That's why NASA and ESA are going with missions now. We really haven't had much information on the surface since Magellan. So yeah, we're sort of scraping at the old data, but finding still really good stuff in it.
Very nice. Well, it'll be really exciting over the next couple of years to see these missions come off and this new data come down, and we'll learn even more about the surface. Very cool.
Yeah. And I'm hoping that we can lure Andriana back into research at some point. I mean,
I hope so.
I think she's doing a wonderful thing now, working for an environmental company. You get a lot of interesting, useful experience working in industry. And then if you decide to go back into research, that's just incredibly valuable. So anyway.
Cool.
Yeah, I was just gonna say my love for research is still there. I just need a break from the school stuff and try something new for a little bit, catch up on field trips that I missed from COVID.
Understood.
Like that.
I understand that. I did the same thing. So it's cool.
It's cool. Yeah.
All righty. Andriana, Allan, thank you once again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.